is the outline of our discussion. I will be discussing first the leading coefficient test, the real zeros of polynomial, and also the repeated zeros. Now, these three concepts here are very important when we move on to the discussion on how to sketch the graph of a polynomial function, because we knew already that a polynomial function has degree n, right? So if we'll be given a polynomial function of degree 100, for example, can we still sketch the graph by not using a software? Yes, we can still sketch the graph. All we have to do is just to follow the rules and the techniques and the procedures on how to sketch a polynomial. So we start with the leading coefficient test. Now, the leading coefficient test is a test to determine the end behavior of the graph of the polynomial function. So this is the polynomial function, right? So this test will tell us the behavior of the graph of the polynomial function. Okay. Now, since we know that a polynomial has degree n, so we have to identify whether our n is odd or even. Now, in the case that our n is odd, okay, so if n is odd, the next thing that we are going to do is to identify the leading coefficient. So here, uh, if p has an odd degree, the polynomial function has an odd degree, and the leading coefficient is positive, then the graph looks like this. It looks like what? It looks like x cubed. Okay? So here, y approaches to infinity as x approaches to infinity. Okay? Y approaches to infinity as x approaches to infinity, and y approaches to negative infinity as x approaches to negative infinity. Or I always say this one to my students, that for us to remember, we can also say that it starts from what? It starts from southwest and it ends here in the northeast. Okay? Now, if a polynomial has a degree of odd, but the leading coefficient is negative, so the graph looks like this, meaning y, okay, y approaches to positive infinity as x approaches to negative infinity. And in this case, in this part here, y approaches to negative infinity as x approaches to positive infinity. Or it starts from northwest and it ends here in the southeast. Okay? Now, what will happen if we have a polynomial whose degree is even? So if the degree is even and the leading coefficient is positive, then the graph looks like this, which means that y, so in this side here, y is approaches to positive infinity as x approaches to negative infinity, or to the left, while it approaches, or the y value approaches to positive infinity as x approaches to positive infinity, or as x goes to the right. Okay? Okay, or we can also remember by saying it starts from northwest and it ends in the northeast. Okay? But how about if the polynomial has degree which is even and the leading coefficient is negative? Then the graph looks like this, which means that the positive value, the y values approaches to negative infinity as x approaches to negative infinity. While here also the y value approaches to the negative infinity as y approaches to positive infinity, or it starts from southwest and it ends here in the what? Southeast. Okay? So here is a um like a summary. Okay, it's a mnemonic device. So for example, even degree and the leading coefficient is positive, which is greater than 0. So the graph starts here from northwest going to northeast. If it has a negative leading coefficient and the degree is even, still even, then it starts from southwest going to what? Going to southeast. Okay? But if the degree is odd, okay, and the leading coefficient is positive, then it starts from here going here. So it starts from northwest, no, sorry, southwest, okay, and it ends here in northeast. While if the leading coefficient is negative, then it starts here in the northwest going to southeast. Okay, another way to remember the behavior or the end behavior of the graph is just by comparing it to the basic function like x squared and x cubed. So x squared has a degree 2, which is even, right? So it starts from here and it ends here. Okay? If the leading coefficient is negative, then x squared x squared is what? The opening of x squared is downward. So that's why it starts here and it ends here. Okay? Or if the degree is odd, for example, we compare it to x cubed. X cubed, if the degree is positive, then it starts from here going here, right? Okay? And if the leading coefficient is negative, it starts from here going here. Okay? So those are the ways or mnemonic device that we can use in order to remember the behavior or the end behavior of the graph of a polynomial function. So for us to understand more on the concept, we have here examples. So for example, number 1, f of x is equal to negative x cubed plus 4x. So we have to identify the degree of this polynomial function. The degree is 3, which is even. Which is odd. The degree is odd and the leading coefficient is negative. Okay? So we expect that the graph starts from here and it ends here. So from north west, okay, going to southeast. Okay? How about this one? F of x is equal to x raised to 4 minus 5x squared plus 4. The degree is 4, which is even. So we expect that the graph looks like x squared, right? So it starts from here, okay, and it ends it here. Okay? So how about this one? F of x is equal to x raised to 5 minus x. The graph looks like x cubed. Okay, since we have the degree which is odd and the leading coefficient is positive, so it starts from here, from the southwest going to northeast. Okay? So, next is real zeros of polynomial. Since we already knew on how to sketch the graph of a polynomial by just identifying the behavior of or the end behavior of the function or of the graph, we also have here finding the real zeros of polynomial. So we have to know what is a real zero or what are zeros of the polynomial and how can we get the zeros of the polynomial. So if f is a polynomial function and a is a real number, the following statements are equivalent. So if we have x is equal to a, then x is equal to a is a zero of the function f. Or This is also equivalent by saying that x is equal to a is the solution of the polynomial function f of x is equal to 0. So which means if we are asked to find the solution of the polynomial function, all we have to do is just to equate the function to 0, then we solve for x. And the values of x, okay, are the solutions or the zeros of the function. Now, quantity x minus 1 is a factor of the polynomial f of x. Okay? For example, we have f of x is equal to quantity x minus 4 raised to 3. Then that x minus 4 is a factor of the polynomial function. Number 4, the ordered pair a and 0 is an x-intercept. A here is a specific value for x. For example, 1 and 0. So 1 and 0 is an x-intercept. Okay? X-intercept is the value of um, the the value of um, x, okay, in which the graph touches on that value in the x-axis. Okay, so we have here example. Let p of x is equal to x squared plus x minus 6. Find the zeros of the given polynomial function. So how can we find? We have the solution. First, we have to factor this out. That is, p of x is equal to quantity x minus 2 times x plus 3. Okay, after factoring this out, we have to solve for x by we have to equate this one to 0 first and solve for x. Okay, from the factored form, by factoring this polynomial function, we come up with this x is equal to 2 and x is equal to negative 3, which are zeros of p, of polynomial function p. Okay, so these are the zeros, meaning these are the values that can make the function 0. Number 2, x is equal to 2 and x is equal to negative 3 are solutions of p, because solution and also zeros are equivalent. Now, x minus 2 and x plus 3 are factors of x squared plus x minus 6. So we have two factors, x minus 2 and x plus 3. Number 4, x is equal to 2 and x is equal to negative 3 are the x-intercepts of the graph of P. Or if we write this in an ordered pair, we have 2, 0 and negative 3, 0. These are the x-intercepts of the graph of P. Okay, so we have here important remarks. The function f, or which is the polynomial function f, has at most n real zeros, and the graph of f has at most n minus 1 turning points. Because knowing the end behavior of the function is not enough. So we have also to know how many zeros that a function has or how many turning points. So for example, let's go back to these examples here. In the first example, the function f has at most n real zeros. Okay, so we have n, which is the degree, which is 3, has at most n real zeros. How many zeros do we have? So these are the values of x, right? Okay, that the graph, okay, the graph touches to this what? Touches or crosses these values, these real zeros. So we count the real zeros. These are the real zeros, this point here, and this point. Meaning we have how many zeros? We have 3 zeros. In this case, we have exactly 3 zeros. Okay? So when we say at most, which means the maximum value of zeros, is n. Okay, so in this example, how many zeros do we have? This point here, this point, this one, and this one. So in this case, we have 4 zeros. Okay, 4 zeros. Again, to find the zeros, we equate this one to 0, then we solve for x. Now, how about this? How many zeros do we have? By just looking at the graph, we only have 1, 2, 3, right? 3 zeros. By just looking at the graph, 3 zeros only. That's why um, that's why it is at most, meaning it is less than or equal to n. So in this case, 3 zeros, but we will understand why we only have 3 zeros, because there are zeros here that are repeated. Okay. Now the graph of f has at most n minus 1 turning points. By the way, n minus 1 turning points, in this case, we have how many turning points? 3 minus 1. So we should have 2 turning points. So these are the turning points. 1, 2. In this case, how many turning points? 4 minus 1. So we should have 3 turning points. So we have 1, 2, 3. Okay? How about this one? We have 5. So 5 minus 1. So we should expect what? 5 minus 1, it is 4, right? But we only have 2 turning points. That's why we use the word at most. It should be less than or equal to the, it should be less than or equal to n minus 1. So in this case, we only have um, 2 turning points. At most, meaning less than or equal to. Okay, so what do we mean by repeated zeros? A factor, quantity x minus a raised to k, where k is greater than 1, k is the exponent, yields a repeated a zero, x is equal to a of multiplicity k. So for example, we have x minus 2, quantity x minus 2 raised to 4. Okay, 4 is greater than 1, right? So it yields a repeated zero of x is equal to 4 of multiplicity 4. Okay, so number 1, if k is odd, the graph, so the exponent, if k is odd, the graph crosses the x-axis at x is equal to a. Okay, the graph crosses the x-axis at x is equal to a. If k is odd, it crosses the zeros at x is equal to a. So if we go back to the example that we have, okay, so the graph crosses to, since the exponent is odd, so it should cross here in the values of x, this x value, this x value, and this x value. Now, if k is even, the graph touches the x-axis at x is equal to a. Okay, for example, x squared. So x is equal to 0 is the 0. Therefore, the graph touches at x is equal to 0. Okay, if k is even. So let us have here an example, a specific example. F of x is equal to quantity x minus 3 raised to 6. Now, notice that k is equal to 6, right? Which is greater than 1. And the function yields a repeated 0, x is equal to 3. So we read this one at x is equal to 3 of multiplicity 6. So how many times we have, this is repeated 6 times. X is equal to 3 is repeated 6 times. Since the k value is 6, which is even, then the graph touches the x-axis at x is equal to 3. So let us see if the graph really touches at x is equal to 3. Okay, so let us count. This is 1, this is 2, this is 3. And we are correct that the graph touches only at x is equal to 3. And it looks like what? It looks like x squared, the graph of x squared. Okay, so we have here practice problem. If you want to practice more, so I have here a problem. Find all the real zeros of the polynomial. Okay, this one. Then after finding the zeros, determine the number of turning points. Okay, determine the number of turning points. So by sketching the graph, we can determine the number of turning points, especially if we will be given a function whose degree is odd. It's difficult. It's quite difficult to determine the number of turning points, right? Unlike the polynomial function whose degree is even. Okay. Now the graph of that function is this one. So since this is a practice problem and the graph is already given, I just want you to solve only the zeros and also the number of turning points. Okay, then after that one, you sketch the graph. Okay, by not looking at this graph, then after sketching, you compare your graph to this graph. Okay. Another practice problem, find all the real zeros of the polynomial. Okay, so how to find the real zeros of the polynomial? You have to equate this first to, or you have to factor this out first, then you equate that to 0, then you solve for x. Then determine the number of turning points. Okay, determine the number of turning points. And again, the graph is already given. So for you to practice, you have to solve this. Use a piece of paper, ball pen, and try to solve. Then after that, you compare your answer or you compare the graph, your graph to this graph. Okay, so that's it. That's another way of sketching a polynomial function using the leading coefficient test and also the finding the zeros of the polynomial. So hope you like this video and don't forget to share the learning that you've got from this video. So thank you once again and God bless.